Well, let's consider what would happen if you wanted to rotate around a different axis. Because in your book, for example, you've got the moment of inertia of a sphere and it's around the center of mass. Or you've got the moment of inertia of a rectangular object and it's around its center of mass. Okay, you've got, for example, a long, skinny rod around its center of mass. But what if you had two spheres and they were rotating about the common point between them? This would be, for example, like contact binary stars. Or suppose you're swinging a rod around the end point. Or suppose your rectangular block here is, instead of going around the center of mass, is going around some spot over here about halfway between the end and the center of the mass. So what would be the moment of inertia of those systems? Now, you could do this the hard way, and that is you could actually go ahead and do the triple integral of rho r squared dx dy dz using the different limits of integration right there for each of those. Okay, well, let's do that just yet. Okay, because no one wants to do that because that's hard. Okay, so let's consider, for example, we've got some object here and its center mass is here and someone has already calculated I around the center of mass. And they did that by putting coordinates right here at the center of mass. Okay, and so this is going to be your coordinates, the center of mass coordinates, x and y. Okay, and so for every little dm out here, there's going to be some x and some y position right here. Okay, and we'll call it x prime and y prime because we'll call these the primes, that being the coordinate relative to the center of mass. Okay, so someone has already calculated this, and so that is going to be this integral of rho squared r squared dx dy dz. Okay, where r squared here, I'm going to call it r prime squared because that's just in the center of mass. So r prime squared is going to be x prime squared plus y prime squared. Okay, so, and then that's been done for you, let's say, and it's in a table. So like in the textbook, there's a table and it says that this is sum equal to like I prime. Okay, or I'm going to call this maybe I CM or even I naught. So that's the I around the center of mass. Okay, so now that's been done for you, but you aren't interested in that. You, center of mass is here, so we know the center of mass around that point. You are interested in rotating around that spot. Okay, so now you're going to have a different x and y coordinates. This was x prime and y prime around the center of mass. So we have something up here, and so now the I is going to be the integral, and just assume this is a triple integral of rho squared, r squared, we'll just do r squared dm. Okay, because you know that the integral dm is really the triple integral. Okay, so there it is. Now r is going to be that. So r, we're going to say that there's an x naught and a y naught for the center of mass. So that means that r squared is going to be x squared plus y squared, but x is going to be x naught plus x prime, and y is going to be y naught plus y prime. Okay, where x naught and y naught are the coordinates of the center of mass relative to the axis we're rotating around, and x prime and y prime are the coordinates relative to the center of mass. Okay, now remember before I naught, which is around the center of mass, was integral of r prime squared dm. So the r prime squared was the x prime squared plus y prime squared. Okay, but we don't want that because that's going around the center of mass. We want to go around this other axis. So that means we need to include this r in our calculation. Okay. So that means that I is going to be the integral of r squared dm. So that's going to be the integral of x squared plus y squared dm. So that's going to be the integral of, well, that's the integral of, we can actually separate this thing out. So we can separate it out and say this is the integral of x squared dm plus the integral of y squared dm. Okay, so that is going to be the integral of x naught plus x prime squared dm plus the integral of y naught plus y prime squared dm. So this becomes the integral of x naught squared plus 2x naught x prime plus x prime squared dm plus the integral of y naught squared plus 2y naught y prime plus y prime squared dm. Okay. So now what we can do is we can collect all our terms. So we can now do algebra. So this is going to be the integral of x naught squared plus y naught squared dm plus the integral of x prime squared plus y prime squared dm plus the integral of 2, the integral of x naught x prime dm plus 2 times the integral of y naught y prime dm. Now let's look at it. What is that? Well, for our center of mass is right here. Our axis of rotation is right there. So that's x naught, that's y naught. So what we found was that quantity right there. Okay, so what is that quantity right there? That quantity, that thing right there is, I'm going to just call that capital R. That is how far the axis of rotation is from the center of mass. Okay, so that would be that would mean that our I is just going to be equal to, and that's a constant. That's a constant. So that, I mean, as this thing rotates, that R is a constant value, so it comes out of the integral. So we just have R squared integral dm. Okay, now what's the other integral? Well, x prime and y prime. So this other integral over here, the second integral over here, is the integral of r prime squared dm. Okay. But wait a minute. Integral of r, we know that the integral of r prime squared dm is just I naught. So that's just the moment of inertia around the center of mass. That's already been calculated. So that means we know what this value is. By the way, what is integral dm? Integral dm is just m. Okay, so integral dm is just m. Now, what about the other two integrals? So we have 2 integral x naught x prime dm. So this comes out of the integral. And so what we have is the coordinate of the x coordinate of the center of mass in center of mass coordinates. Well, what's the x coordinate of the center of mass if you put your origin in the center of mass? 0. Poof. That's nothing. Okay, so what's the other one? Well, the other one is going to be the same thing. It's going to be the y coordinate of the y center of mass it's the y center of mass coordinate in the y center of mass coordinates axis. So that's where when the origin is put at the center of mass. So that also is 0. So I would call that integration by obliteration. Okay. So now we have this down so that I is just going to be equal to mr squared plus I know. What does that mean? It means if you have an object and you already know what the I is around some axis, if you want to go around a different axis, then what you do is you imagine this thing is going around. And if you think about it, as it goes around, it changes orientation. And so it's going to be as if it's going around and the center of mass is going around. So this is going to be the moment of inertia of the center of mass going around, and that's going to be the moment of inertia of the thing rotating. And so we call this the parallel axis theorem. Parallel axis theorem says that the moment of inertia is simply going to be the moment of inertia of the center of mass going around versus the plus the moment of inertia of going around the center of mass. Okay, so the very next problem, we'll do an example showing that. Or very next, not problem, but very next lecture, I'll do an example of that.